All right, welcome back, everyone. I'm absolutely thrilled to have you here for another explainer. Today, we're tackling one of the most notorious challenges in back-end engineering. I want you to imagine this. It's the busiest shopping day of the year. Your servers are humming, traffic is spiking, and a customer clicks buy on that massive, big-ticket item. But right at that precise millisecond, a network cable gets unplugged, or maybe a server just crashes. Well, an engineering nightmare is about to unfold.
Think about it. What happens when a payment succeeds, but the order creation fails? The customer's credit card has been charged, the money is gone, but the item isn't shipping. Why? Because the independent systems running your application completely disagree on the outcome. This right here is the terrifying reality of partial failures in distributed systems. When you split your app into microservices or you partition your databases, these independent nodes, they don't share memory. They don't magically know what the other is doing. So when things go wrong, you are left with a massive, inconsistent mess.
So, here's our roadmap for today. We'll start with the distributed transaction dilemma, then look at the anatomy of a checkout. Next, we'll get into two-phase commit explained, followed by the coordinator's crucial role. Then we'll stress test things with failures, blocking, and uncertainty. And finally, wrap up with the cost of correctness. Let's dive in.
Okay, Section 1, the distributed transaction dilemma. Fundamentally, a distributed transaction is just one logical operation that spans across multiple databases. The goal? Strict atomicity, meaning everything commits or everything rolls back, nothing in between. And honestly, this is incredibly tempting for developers. You have one single business operation, like buying a pair of shoes, and you desperately want the safety and guarantees of a single database transaction, right? Wrapped up in a neat little package. But you want that exact same magic stretched across a massive, horizontally scaled, partitioned architecture.
Moving to Section 2, Anatomy of a Checkout.
Let's actually break down a standard e-commerce checkout into 4 distinct steps to see why this matters so much. Step 1, charge the payment. Step 2, reserve the inventory. Step 3, create the order. And Step 4, update the shipment. Imagine your code successfully executes Step 1 and Step 2. Boom, the database logs the payment, the inventory is reserved. But then, a catastrophic crash happens right before Step 3. Your system is now in an incredibly dangerous, inconsistent state. The money is taken, the shoes are reserved in the warehouse, but there's literally no order tied to the customer. We desperately need a mechanism to ensure all these steps either succeed together or fail together as one single atomic unit.
Which brings us to Section 3, two-phase commit explained.
To save us from those nasty partial failures, the industry standard has long been the two-phase commit. As the name heavily implies, 2PC is an atomic commit algorithm split into 2 distinct phases. There's a prepare phase and then a commit or abort phase, executed across multiple nodes. Now, to make this whole dance actually work, 2PC introduces a critical new component that you just don't see in a standard single-node setup. It introduces a coordinator. Sometimes you'll hear it called a transaction manager, which steps in to orchestrate the entire process.
Section 4, the coordinator's crucial role.
This coordinator entirely dictates the fate of the transaction. It starts by assigning a globally unique transaction ID. This ID travels with every single read and write across all the independent databases, securely binding them together. So, Phase 1 kicks off. The coordinator sends a prepare message to all participating databases. It's basically asking them to definitively check for conflicts, check their constraints, and most importantly, write the transaction data to durable storage on disk. A node can't just casually say it's ready. It has to be absolutely certain it can commit under any circumstances, even if someone trips over the power cord a second later.
A really great way to think about the 2PC prepare phase is like a traditional Western marriage ceremony. The coordinator is essentially the minister. The minister asks the participants if they are ready to commit. When a database votes yes in the prepare phase, it's exactly the same as saying, I do. By saying yes, that participant completely surrenders the right to unilaterally abort the transaction later. They are making a binding promise that they will commit if the coordinator tells them to.
Let's walk through the happy path here. Up at the top, we've got our coordinator, talking to Database 1 and Database 2. First, the application writes the data. Then, Phase 1 begins. The coordinator sends out that prepare request. Both databases do their disk writes and vote yes. Awesome. Once the coordinator collects all those yes votes, we hit what's called the commit point. This is where the coordinator writes its final decision to its own log on disk. Then we jump to Phase 2. The coordinator sends the actual commit command. Everyone acknowledges, and the transaction is successfully completed. Honestly, it looks beautiful on a whiteboard, doesn't it?
But of course, things go wrong. Section 5, Failures, Blocking, and Uncertainty.
So what actually happens when messy physical reality hits this elegant system? Well, let's start with a safe failure. If a database participant times out during phase 1, or if it checks its constraints and just votes no, maybe because, hey, inventory ran out, the system is perfectly safe. The coordinator simply says, okay, we don't have unanimous consensus, and sends an abort command in phase 2. Everything rolls back, no harm, no foul. Our atomicity is completely maintained.
But okay, pay close attention to this, because this is the real climax of our explainer. What happens if the coordinator collects the yes votes, decides to commit, but then violently crashes before it can actually tell Database 1? Database 2 got the commit message, sure, but Database 1 is left completely in the dark. Remember, it already said, I do. It surrendered its right to abort, but it hasn't received the final verdict. Database 1 is now trapped. It enters a state known technically as in doubt or uncertain. It cannot unilaterally abort, and it can't unilaterally commit. It is completely, hopelessly stuck.
And this leads us to a fundamental definition. Two-phase commit is a blocking atomic commit protocol. What that means is, by design, participants can become permanently stuck waiting for a crashed coordinator to recover. Because Database 1 is in doubt, its only possible path forward is to just sit there and wait for the coordinator to eventually reboot, read its own transaction log, and finally resend that missing commit or abort message.
And the collateral damage here is truly terrifying for a back-end engineer. Notice the warning here. Database locks are held. While that database is stuck in doubt, it must maintain all the locks on the rows it modified. If your coordinator takes 20 minutes to recover, those rows are fully locked for 20 minutes. Any other transactions that need to read or write to that same data? They are completely frozen out. Your system's availability just starts plummeting simply because it's waiting on a dead coordinator.
Finally, Section 6, the cost of correctness.
Look, the pros of distributed transactions are undeniable. You get strict atomicity and strong consistency. But when you look at the cons, the costs are absolutely massive. You introduce severe network latency because of all that synchronous back-and-forth messaging we just talked about. You introduce the huge risk of blocking, and you add an immense layer of operational complexity. By trying so hard to eliminate partial failures, you've ironically introduced a critical single point of failure into your system, the coordinator itself.
In practice, these turn into massive operational nightmares. Two-phase commit actually tends to amplify failures. Think about it. If one minor node has a network hiccup, the entire distributed transaction fails. And remember those orphaned in-doubt transactions holding locks? If the coordinator's log gets corrupted and it literally can't recover, the system cannot resolve it automatically. It requires a highly stressed database administrator to log into the production system during a massive outage and manually apply heuristic decisions to force those locks open. It drastically reduces your overall system availability.
So, I want to end our explainer today with a pretty provocative question for you to ponder. Is the guarantee of absolute correctness, that dream of a perfectly atomic distributed transaction, actually worth the risk of bringing your entire system to a halt? As we've seen from the source material, a lot of modern architectures decide it just isn't, opting instead for asynchronous coordination and looser constraints. But, that's a system design trade-off only you can make for your specific application. Thank you so much for joining me today. I really hope this helped clarify the complex world of distributed transactions. Keep building, keep learning, and I'll see you in the next explainer.